Okay, so we have been looking at the capillary filling process. So, I have looked at how the interface of the liquid changes at the beginning of the filling process. Let us look at what happens at the end of the filling process. Okay. So, we look at capillary filling. And we will look at what happens at the end of the filling process. Okay. So, we said that at the end of the filling process the inertia and the surface tension are negligible. Okay. So, the inertia and the surface tension forces are negligible. So, in the general equation if you drop off the inertia and surface tension forces, then we get 4 nu over g r square into d of x square over dt plus x minus x infinity as 0, where we say that x infinity is x 0 plus L. Okay. So, now if we consider a parameter x as x infinity minus capital X, we can say that d x square over dt at x tends to 0 will be 2x into dx, which will be equal to minus 2 x infinity into x. Okay. So, this is what we can say. So, now in this equation we can write this as 8 nu over g r square into x plus x is going to be 0. Okay. So, this equation is very easy to solve, right. So, we can find a solution for x. T is going to be x infinity exponential minus r square g over 8 nu x infinity into t. Okay. Now, if you convert it back to the original variable x, capital X, so x t can be written as x infinity into 1 minus exponential minus r square g over 8 nu x infinity into t. Okay. Now, we can convert it back to the small x t, which is our original variable. X t is going to be L minus L plus x 0 exponential minus r square g divided by 8 nu into L plus x 0 into t. Okay. So, that is the solution we would have at the end of the filling process when t tends to infinity. Okay. So, what we see here is that the profile is going to reach a steady state exponentially. Okay. So, the x t varies as exponentially Okay. So, we can define a time constant for the filling process which will be given by this expression. So, this is a time constant. So, it is actually inverse of t 1 over tau. So, we can define a time constant of capillary filling okay. So, tau rising 8 into L plus x 0 nu divided by r square g. Okay. So, the time constant is an indicator of how much time it is going to take for the capillary rise to occur. So, that is the observations that we make for the capillary filling in case of a vertical tube. Now, let us talk about for a horizontal tube case. So, for the dynamics of passive capillary in horizontal configuration. So, for horizontal configuration, of course, the gravitational force will be negligible. So, the gravitational force is neglected. Okay. And in that case x 0 is going to be 0. Okay. So, what we defined x 0 as. So, if you look at here, we defined x 0 as the the portion of the capillary which is dipped inside the liquid container. Since here we are talking about a horizontal tube, the x 0 is going to be 0. So, here x 0 is 0. So, from the general equation we can simplify by dropping up the gravitational force and putting x 0 equal to 0. So, the equation that we would have is d square x over dt square plus 1 over x into dx over dt square plus 8 mu divided by r square rho into dx over dt plus g minus 2 sigma L g into cos theta divided by rho r x is going to be 0. Now, we can drop off the gravitational force. So, we can write d square x over dt square as minus 1 over x dx over dt square minus 8 nu over r square into dx over dt plus 1 over x 2 sigma L g cos theta divided by rho r is going to be 0. Okay. So, the term 1 over x into dx over dt square, okay, because we are talking about a horizontal tube and where the velocity, and we are talking about capillary flow where the velocity is very small and this term is squared here, okay, this term is going to be negligible. Okay. So, this term is going to be negligible. So, you can simplify the equation further where this term vanishes. So, d square x over dt square will be minus 8 nu over r square dx over dt. So, plus 1 over x 2 sigma Lg cos theta over rho r. Okay. Now, we can write the initial conditions. The initial condition are x at t equal to 0 is going to be 0 and dx over dt at t equal to 0 is going to be 0. Okay. So, that is at the very beginning of the capillary rise advancing process. So, if you substitute x equal to x square in the above equation. So, this equation would reduce to, so d square capital X over dt square plus alpha into d capital X over dt will be equal to beta. Okay. And here alpha would be 8 nu over r square and beta would be 4 sigma Lg cos theta over rho r. Okay. Now, this equation is easy to solve. So, you can find a solution for this. So, the solution would be x will be square root of capital X, which is beta over alpha square into exponential minus alpha t plus beta t over alpha minus beta over alpha square, okay, square root. So, that is how x is going to vary with time. Okay. So, x is a function of time. So, from there we can obtain an expression for the velocity. Okay. So, the velocity of the interface u as a function of t is going to be beta. So, you can find dx over dt there. So, it will be beta into 1 minus exponential minus alpha t divided by 2 alpha x. Okay. So, that is the expression for the velocity. Okay. So, we have looked at two cases, one vertical tube case where at the beginning of the filling process the interface is going to follow as square root of t, and at the end of the filling process is going to vary as the exponential of time. And we have also looked at that for the horizontal case where that is the profile is going to vary as exponential of the time. Okay. So, now let us move on and talk about transpiration cooling. Okay. So, transpiration cooling is what we see on the leaves. Based on that, the water moves from the root of the tree to the leaf, because the water moves out of the leaf because of the transpiration cooling effect, and it creates a negative pressure on the surface of the leaf, which basically draws liquid from the ground to the leaf. Okay. So, similar effect that is discussed here. So, we have a liquid reservoir in which a liquid is present, and so by capillary action the liquid is allowed to go through this capillary until a point where we have a hydrophobic patch. So, this area of the capillary has got a hydrophobic patch. So, the liquid forms a meniscus there, okay. After the capillary filling, the liquid form a meniscus, and here we apply the heat, okay. So, this is the heat that we are at the interface, and because of which the evaporation occurs, and the air coming in here picks off the vapor and exits, and this process repeats as long as we have an interface there, okay. And as the air carries this vapor, it creates a negative pressure, and the liquid from the reservoir continues to draw into the interface, okay. So, what we have here is liquid in a reservoir which is drawn into a capillary. So, liquid from the reservoir fills horizontal channel, and this is due to capillary effect. And the meniscus is stopped using a hydrophobic patch. Okay. So, and we are heating the meniscus. So, the liquid heating is done at the meniscus, and this increases the vapor pressure. At the interface, okay. So, we would have air from an external source, and the air will carry the liquid vapor, and that would create a vapor pressure gradient, okay. That will create a gradient of pressure, okay. So, that will enable the liquid to come in continuously to the interface. So, liquid comes in from reservoir to interface continuously, okay. And that velocity is given by this expression m into d over rho r t, and into A into evaporator over A P v minus P v 0 divided by L into 1 plus u 0 d h over d. So, this is the expression for the velocity due to transpiration cooling, okay. So, u is the velocity due to transpiration cooling, m is the molecular weight, and d is the diffusion coefficient, T is the temperature, and rho is the density, R is the universal gas constant, and PV is the vapor pressure at the meniscus, and PV 0 is PV 0 is the vapor pressure at the airflow side. Okay. And the area of the evaporator and the area of the cross section of the channel are given, and the length of the channel is also given here. Okay. So, that finishes our discussion on the transpiration cooling based micro pump. Now, let us consider few examples. Okay. So, this is the first example we would consider. We have a thermopneumatic check valve pump that delivers a maximum flow rate of 340 microliter per minute and a maximum back pressure of 50 kilopascal. Okay. And the heater resistance is 150 ohm. The pump works with a symmetric square signal with a maximum voltage of 1 volt at 0.5 hertz, and we want to determine the pump efficiency. Okay. So, how do we do that? So, first we would have, this is time and this is voltage. So, we have a pulse signal that is being applied. Okay. So, this is applied for only 1/2 of the cycle. Okay. So, we can find out the power of the pump we can find the power of pump as P max. So, this is pump power, P max Q max divided by 2. So, that will be P max is 50 kilopascal, 50 into 10 to the power 3, and Q max is 340 microliter per minute. So, 340 into 10 to the power minus 9 divided by 60 meter cube per second divided by 2. So, that would be 1.42 into 10 to the power minus 4 watt. Okay. Similarly, we can find the heater power. Okay. Now, the heater is actuated only for half of the cycle. Okay. So, the other half, the voltage is not present. Okay. So, we would have P actuator will be equal to half into V square R over R, okay, which is going to be 1 divided by 2 into 150. So, V is 1 volt here, right, and R is 150 ohm, right. So, this is going to be 3 into 10 to the power minus 3 watt. So, you can find the pump efficiency for pump efficiency is going to be the power of the pump divided by power of the actuator, which is the heater power, going to be 1.42 into 10 to the power minus 4 divided by 3.3 into 10 to the power minus 3. Okay. So, this is 3.3 into 10 to the minus 3. So, that is going to be about 0.426%. Okay. So, the efficiency is about 0.426%. Now, let us consider another example. So, we have a check valve pump that has circular orifices as inlet and outlet, and the orifices have diameters of 400 micron, and we want to determine the minimum compression ratio for self priming. Okay. Now, for a check valve pump there are many sources to hold the valve in place. We have the spring force, or we can have thermopneumatic force which can hold it in place. Okay. So, we will have many sources like spring force, van der Waals force, or we can have capillary force. Okay. So, these are different sources that can be used to close a valve. Okay. Now, for a valve that is handling liquid, since the condition is moist, the capillary force based valve closing is most significant. Okay. So, this becomes most significant in moist condition. Okay. So, this has the biggest impact in moist condition. Okay. So, these are the sources which can close the valves. So, the surface, since we are telling that in moist condition capillary force is going to be the strongest force, we can find the surface energy. The surface energy of a wetted inlet orifice of wetted inlet orifice. So, what is going to happen is this. Okay. So, you have a valve port something like this, and here this is, let us say, the valve seat. So, you have this tiny gap between the the valve seat and the valve actuator. Okay. So, this gap, let us say Z. So, in moist condition when this is handling liquid, you would have a liquid film sitting here, right. So, there is a liquid film sitting here. Now, if you want to open this valve, the applied energy has to overcome the surface energy that is already created because of the presence of this liquid here. Okay. Now, so we can find what is going to be the surface energy of an wetted inlet orifice, and the applied force has to overcome this force. Okay. Many times when we are talking about two metting surfaces, if let us say this is dry and this surface is metting there, in some cases you have some spring force that is trying to close the valve. So, the applied force has to overcome the spring force, or in some cases if there is no spring present, but we have just the valve actuator is physically in contact with the valve seat, there is van der Waals force. So, to separate that you have to overcome this van der Waals force, which are normally very weak forces. Okay. But in this case, since we are dealing with liquids in microchannels, we would have this liquid interfaces, and the applied force has to overcome the liquid interfaces. So, first we calculate the surface energy of an wetted inlet orifice. So, the U surface is going to be sigma into pi d into z. Okay. So, that is going to be the surface energy. Sigma is the surface tension coefficient and d is the orifice dia and z is the small gap. Okay. So, here we assume that this there is physical contact throughout. So, we get the surface energy as sigma into pi d into z, right. Now, the external force will be applied, okay. So, this would cause mechanical work. So, the external force applied has to overcome the critical pressure that is required to open the valve. Okay. So, the external force, so total work done would be delta P critical, that is the critical pressure to open the valve, into the area which is pi d square over 4 into, so that force is applied over a distance z, okay, since it tries to open that. So, this is the energy that is supplied, right. So, this work has to be greater than the surface energy that is trying to prevent this actuator to open up. Okay. So, for the valve actuator to open, W has to be greater than the U surface. Okay. So, if that is the case, what you would get in the limiting case, this will be equal to the surface energy. So, delta P critical into pi d square over 4 into z has to be equal to sigma pi d z. Okay. So, we can find here sigma will be equal to, sorry, we can find the delta P critical, the delta P critical is going to be 4 into sigma over d. Now, knowing the critical pressure, we can find the compression ratio. So, the surface tension of water, considering water as the liquid, considering sigma as 72 into 10 to the power minus 3 Newton per meter for water, we can find delta P critical, that will be 4 into 72 into 10 to the power minus 3 divided by d, d will be 400 micron, it is given. So, 400 into 10 to the minus 6, so that is going to be 720 Pascal. So, we need minimum 720 Pascal to open the valve. Okay. So, we can find the minimum compression ratio, the minimum compression ratio which is psi is nothing but delta V over V 0, right. So, we have an expression for psi for liquid. So, that is going to be 1 over k into delta P critical divided by P 0. So, this is the something that we have seen in the previous lecture. So, this will be 1 over 1.4 into delta P critical is 720 and P0 is the atmospheric pressure, which is 10 to the power 5. So, this will be about 5.14 into 10 to the power minus 3. Okay. So, what it tells is that the stroke volume delta V has to be about 0.5% of the dead volume. Okay. So, then only the valve seat will open and it will get, the pump will get self primed. Okay. So, next we consider another example. We consider an example of a peristatic pump that has got 3 pump chambers and 3 circular piezo disc actuators, and the pump membrane has a diameter of 4 millimeter, okay, and the pump works with a frequency of 100 hertz, and we want to determine the volume flow rate at 0 back pressure, okay, given that the maximum membrane deflection is 40 micron. Okay. So, first we can assume, make an assumption that the deflection of the membrane follows that of a thin circular plate. So, the deflection of membrane follows deflection of a thin circular plate. So, in that case we can write the deflection YR as Y0 to 1 minus R over R square whole square. So, we can find the maximum volume that the pump chamber can take. So, the maximum liquid volume the pump chamber can take, which is given by delta V will be twice 0 to 2 pi into 0 to R Y0 into 1 minus Y over R square whole square R dr into dr into phi. So, basically what we are trying to do here is, let us say this is the undeformed position of the membrane and this is the deformed position. We are trying to find what is going to be this area. Okay. So, that will be the stroke volume, right. So, the membrane is actually, this is the volume that the membrane is storing. So, we take a symmetry about this. So, that is why the factor 2 is coming. Okay. So, we get 2 pi over 3 into Y0 R square. So, that will be 2 pi over 3. The maximum deflection is given as 40 micron. So, this will be 4 into 10 to the power minus 5 into the radius of the membrane is given. So, it is 4 millimeter diameter. So, the radius is 2 millimeter, 2 into 10 to the power minus 3 square. So, that will be 3.35 into 10 to the power minus 10 meter cube. Okay. So, this is going to be the liquid volume the pump chamber can take. Okay. So, in a single stroke, okay, as it is expanding it can only take this much volume delta V. Okay. So, if we know a frequency the frequency and so for known frequency, so frequency equal f, then total flow rate will be f into delta V. Okay. So, total flow rate we can calculate. So, we can estimate total flow rate Q going to be f into delta V. The frequency is given. So, the frequency is 100 hertz, right, 100 hertz into delta V is going to be 3.35 into 10 to the minus 10. So, this will be 3.35 into 10 to the minus 8 meter cube per second, which will be about 2 milliliter per minute. Okay. So, that is the flow rate that the pump can deliver. Next, we consider another example. So, we consider a diffuser nozzle pump, and that has a pump membrane of diameter 10 millimeter, and the maximum deflection is about 10 micron, and we like to determine the volume flow rate if the pump frequency is 100 hertz and the fluid diodicity of the diffuser nozzle structure is known. Okay. So, what we first do is find the volume for stroke. So, that we calculated in the previous example. Delta V is 2 pi over 3 into d max into r square. This is the maximum deflection, right. So, this is going to be 2 pi over 3 into 10 to the minus 6 into the radius of the membrane is 5 millimeter. So, 5 into 10 to the minus 3 square. So, that is going to be 5.24 into 10 to the minus 10 meter cube. So, you can find the volume flow rate. Volume flow rate Q would be 2 into delta V into F square root of diodicity minus 1 divided by square root of eta F plus 1. Okay. So, that is known as the rectification efficiency. So, that will be 2 into delta V we just calculated 5.24 into 10 to the minus 10 into F, the frequency is 100 hertz and the diodicity is given 1.58 minus 1 divided by 1.58 plus 1. So, you can calculate this to be 1.19 into 10 to the power minus 8 meter cube per second, which is 715 microliter per minute. Okay. So, let us consider another example. So, this is a rotary gear pump that we have discussed, and it has the following parameter. It has got 596 micron of gear diameter, and it has 12 number of teeth, and the pressure angle is 20 degrees. Okay. So, 20 degrees pressure angle and 505 micron center to center distance. Okay. And the thickness is 500 micron, which is equal to the channel height, and we want to determine the volume flow rate at a speed of 300 micron. Okay. So, this is a very simple question. So, if you remember the formula, the volume flow rate for a gear pump is given by H into pi n d square by 2 minus c square by 2 minus mg square pi square over 6 into cos phi square. Okay. So, this is the expression for the flow rate for a gear pump. So, H is the channel height. So, it is given, which is 500 micron into pi into n is the RPM, which is 300 into d square by 2, d is 596 square by 2 minus the center to center distance is 515, so square by 2. mg can be calculated by the diameter divided by the number of teeth. Okay. So, mg will be diameter 596 divided by 12 into pi square over 6 into cos square 20. Okay. So, if you do a calculation, we get this as 19.5 into 10 to the power 9 micron cube over minute. Okay. So, this is another example, the last example we will consider in this lecture. So, we want to determine the burst frequency of a water column. So, we are talking about a centrifugal pump which is 2 millimeter long and an average distance to disc center is 4 millimeter. The channel cross section is 100 micron by 50 micron. The contact angle is 30 degrees and the surface tension and density of water are 72 into 10 to the power minus 3 Newton per meter and 100 kg per meter cube. What is the frequency to burst of the same water column? Frequency to burst of the same water column at an average distance of 16 millimeter. Okay. So, first we have to calculate what is the burst frequency when at the distance where the liquid column is located at 4 millimeter, then we can calculate what will be the burst frequency when it will be located at 16 millimeter. Okay. So, the first thing to do is to calculate the hydraulic dia. The hydraulic diameter can be calculated as dH is 4 into area of cross section over perimeter. So, 4 into the channel is 100 into 50, so divided by 2 into 150. So, this is about 66.67 micron, and so we can find the burst frequency. We have the formula for the burst frequency. FB is sigma cos theta divided by pi square rho RA into delta R into dH square root. So, you can substitute the values 72 into 10 to the minus 3 into cos 30 degrees is the contact angle, pi square into 1000 into 4 into 10 to the minus 3 into 2 into 10 to the minus 3. So, this is the density, this is the average location, this is the length of the column into 66.67 is the hydraulic diameter into 10 to the minus 6. Okay. So, that will be about 108.8 hertz. So, you can notice that the burst frequency is inversely proportional to the square of the average location. Okay. So, what we can say that f2 over f1 is going to be r1 over r2 square root. Okay. So, now this is the burst frequency at a location of 4 millimeter. Okay. So, what is going to be at 16 millimeter? We can find f2 at 16 millimeter is going to be f1 into r1 over r2 square root. So, this will be equal to 108.8 into 4 over 16 square root. So, that will be 54.4 hertz. Okay. Right. So, with that let us stop here.